NASA admits its Mars orbiter captured unprecedented images of interstellar visitor 3, Atlas. Yet, as China releases a 302-frame sequence, those high-resolution HiRISE shots remain locked behind a bureaucratic freeze. With planetary defense rumors swirling and scientists sounding alarms, why is the most anticipated space data of the year still hidden? Inside the escalating pressure, silence, and the stakes for science, the truth behind this standoff is far stranger than it seems. Confirmation came swiftly. NASA officials acknowledged that the Mars Reconnaissance Orbiter HiRISE camera captured images of interstellar object 3, Atlas, during its close approach to Mars on October 3, 2025. These images are real, not speculative, and their existence is now a matter of public record. For the first time, a spacecraft orbiting another planet trained its most powerful camera on an object from beyond our solar system, an astronomical milestone. Yet while China's Tianwen-1 probe has already published a full 302-frame sequence of the encounter, NASA's images remain locked away, unavailable to the public or the global scientific community. Questions multiplied as word spread of the data freeze. NASA's explanation is procedural. The US government shutdown, which began on October 1st, forced most non-essential operations to halt, including the processing and release of scientific data. Under federal law, only activities directly tied to spacecraft health and safety could continue. Data from HiRISE, though safely stored, could not move through the usual chain of calibration, validation, and public posting. For weeks, the world waited as the images sat untouched in NASA's pipeline. Transparency became a focal point as competing agencies and international observers watched China move quickly to fill the vacuum. The China National Space Administration released its own Mars orbiter images of 3I Atlas, showing a bright, compact coma, a white dot with a faint halo, captured from roughly the same distance as NASA's planned observations. Although the Chinese images are lower in resolution than what HiRISE can achieve, their rapid publication drew attention to the contrast in transparency and speed. Rumors of a planetary defense alert swirled online and in some media outlets. NASA has not issued any official warning or upgraded alert regarding 3I Atlas. The agency's public statements emphasize that the object poses no threat to Earth, and that the focus remains on scientific discovery. The so-called maximum planetary defense alert appears to be unsubstantiated, fueled more by speculation than by any documented action from NASA's Planetary Defense Coordination Office. Pressure is mounting from multiple directions. U.S. Representative Anna Paulina Luna has gone on record stating that NASA will release the HiRISE images once the government reopens and internal reviews are complete. Harvard astrophysicist Avi Loeb has sent open letters, arguing that science depends on timely access to new data, especially when anomalies might challenge established theories. For now, the images remain under lock and key, their contents known only to a handful of mission staff. The world is left waiting as the stakes, scientific, political, and public, continue to rise. The machinery behind NASA's scientific data pipeline is built on precision, routine, and legal compliance. When the US government shutdown began at midnight on October 1st, 2025, nearly all non-essential NASA operations were forced to stop. This was not a matter of choice or internal policy. The shutdown triggered federal law, requiring that only activities necessary for the immediate protection of life, property, or national security could continue. For the Mars Reconnaissance Orbiter's HiRISE camera, that meant the spacecraft itself remained under constant monitoring, ensuring its health and safety. But the flow of new science data, including the highly anticipated images of 3I Atlas, ground to a halt. Methodical is the only way to describe the process for handling these images. After HiRISE captured its scheduled frames during the comet's close pass on October 2nd and 3rd, 2025, the raw data was stored on board the orbiter, then downlinked to Earth during routine deep space network passes. Normally, these files would be transferred to the HiRISE Operations Center at the University of Arizona, where a civilian team would convert the telemetry, calibrate the images, and run quality checks. From there, the science team would review the processed data, validate the results, and prepare them for public release. Each step is governed by strict protocols, and each requires staff who, during a shutdown, are legally required to remain off-duty unless specifically exempted. No part of this pipeline, from raw data ingestion to calibration, validation, and final posting to NASA's public archives, was classified as essential work. Waivers for exceptions are exceedingly rare, typically reserved for matters of national security or immediate risk, not for routine scientific observation. The only staff permitted to remain active were those responsible for spacecraft safety, not for data analysis or public engagement. Even the routine review and approval of images by NASA's Public Affairs Office was frozen. The shutdown's effect rippled out to public records requests as well. Freedom of Information Act queries, which often provide access to internal emails or mission logs, face their own backlog. No Freedom of Information Act released communications about the HiRISE 3I Atlas dataset appeared in NASA's document repositories during this period, and the standard response time stretched even further as the shutdown continued. This procedural freeze is not unique to the 2025 shutdown. Past events, such as those in 2013 and 2019, followed the same pattern. Emergency releases of data only occurred when required for legal or safety reasons, never for general scientific interest. Without a presidential or congressional override, the rules are absolute. As a result, the HiRISE images, while safely stored and fully acquired, remained locked in the pipeline, untouched by scientists or the public, until the government reopened and the full team could return to work. Public pressure began to mount as the days stretched on without any sign of the HiRISE images. In Washington, Representative Anna Paulina Luna issued a clear statement. NASA would be expected to release the 3I Atlas images as soon as the government reopened and the necessary internal reviews concluded. Her words echoed across science news outlets and social media, amplifying calls for accountability. Luna's demand was not just a procedural request, it was a signal that the image blackout had moved beyond technical delay and into the realm of public trust. She framed the issue as one of transparency, arguing that discoveries of this magnitude belong to everyone, not just the handful of officials who control the data pipeline. Avi Loeb took a more philosophical approach. Outside the halls of Congress, the Harvard astrophysicist, well known for challenging conventional thinking about interstellar objects, sent open letters to NASA leadership and to congressional committees. He argued that science depends on timely access to new data, especially when the evidence might reveal something unexpected. He wrote that science advances by pursuing anomalies that defy old paradigms and gathering new data. 3I Atlas is a gift for discovery. For Loeb, the comet's long, observable arc through the solar system was a rare opportunity, not just for scientists, but for the public and for students who might be inspired to ask new questions about the universe. Loeb's advocacy went beyond technical points. He drew a sharp contrast between what he called the humility to learn and the arrogance of expertise. In his view, openness is not just a courtesy, but a core scientific value. He added, "If we want to make progress, we must be willing to admit what we don't know and let the evidence lead us." His message found a wide audience among journalists, educators, and citizen scientists who saw the 3I Atlas episode as a test of whether big science institutions could keep pace with the public's appetite for discovery. Transparency campaigns multiplied. Advocacy groups and science communicators circulated petitions and open messages urging NASA to publish the images as soon as possible. Many observers pointed to China's rapid release of Tianwen-1 data as a contrast, arguing that United States leadership in space science depends on openness as much as technical prowess. Others warned that prolonged delays could fuel conspiracy theories or erode confidence in the agencies responsible for stewarding humanity's understanding of the cosmos. The stakes were no longer internal. The conflict over the HiRISE images now involved lawmakers, scientists, and a global audience invested in the outcome. Each new statement from Representative Luna or from Loeb added to the sense that the stakes were not just scientific, but civic. The images themselves had become a symbol of transparency, of international rivalry, and of the public's right to witness the unfolding story of the third interstellar visitor ever recorded. In this climate, every day that the data remained locked away only sharpened the demand for answers. October 3, 2025 offered an observational opportunity. As 3I Atlas swept past Mars at a distance of 29 million kilometers, the geometry placed the interstellar visitor within reach of some of the most advanced cameras sent beyond Earth. For HiRISE, the high-resolution imaging science experiment aboard NASA's Mars Reconnaissance Orbiter, this was a test of both engineering and timing. The camera had a 50-centimeter aperture paired with a 12-meter focal length, designed to resolve features on the Martian surface smaller than a meter across. But at tens of millions of kilometers, even HiRISE faced the limits of physics and distance. The scientific value of this window was clear from the start. 3I Atlas is only the third object ever confirmed to enter the solar system from interstellar space. Unlike its predecessors, it would pass close enough to a major planet to allow direct imaging by an orbiting spacecraft. With HiRISE's optical system, the goal was to capture the structure of the comet's coma, measure its brightness profile, and refine its trajectory with unprecedented precision. Each frame offered a chance to test models of cometary activity, probe for signs of jets or outbursts, and search for any hint of structure that ground-based telescopes could never resolve from Earth. HiRISE's technical edge was significant. At Mars distance, the camera could, in theory, achieve a pixel scale of about 18 to 30 meters per pixel for a target like 3I Atlas. That is at least twice as sharp as what China's Tianwen-1 orbiter could deliver with its 38.7 centimeter high-resolution imaging camera, and far beyond the 120 kilometers per pixel scale of Hubble's best efforts from Earth orbit. In practical terms, HiRISE was the only instrument in position to capture the comet's inner coma with enough clarity to measure its brightness profile and possibly detect subtle asymmetries or fragmentation events. The timing of the flyby was no accident. Months of planning went into synchronizing HiRISE's imaging schedule with the comet's closest approach. Mission engineers calculated the precise trajectory, accounting for the comet's high speed and faintness. Exposure times had to be short, often less than a second, to avoid motion blur, and the camera's tracking system was pushed to its limits. Even so, the faint nucleus of 3I Atlas would remain unresolved, appearing as a bright point surrounded by a diffuse, compact coma. No instrument currently orbiting Mars or Earth could hope to reveal surface detail on the nucleus itself at this distance, but HiRISE could still provide the sharpest view of the comet's envelope and its immediate surroundings. The urgency behind this observational campaign stemmed from the rarity of the event. Opportunities to image an interstellar object from another planet's orbit are vanishingly rare. The data promised not only to refine models of interstellar comet behavior, but also to set a benchmark for future missions and international collaborations. As China's Tianwen-1 team moved quickly to release their own images, the scientific community watched NASA's HiRISE dataset with anticipation, knowing that even modest gains in resolution could unlock new insights about the nature and origins of 3I Atlas. The window had closed in a matter of hours, but the questions it raised and the data it produced would shape planetary science for years to come. Tianwen-1 moved quickly after the October 3 Mars flyby, releasing a complete 302-frame image sequence of 3I Atlas to the global scientific community. Each frame captures the interstellar object as it appeared from Mars orbit, roughly 29 million kilometers away, using the Orbiter S high-resolution imaging camera. The result is a time-lapse animation that tracks the Comet S progress against the blackness of space, frame by frame, as it sweeps past the red planet. The images reveal a compact, intensely bright core surrounded by a faint, diffuse cloud, the classic signature of a comet's coma. Even at this distance and with an aperture of 38.7 centimeters, the nucleus remains unresolved, appearing in each frame as a white dot enveloped by a subtle halo of dust and gas. The sequence provides no hint of surface features or jets, but it does allow researchers to measure the Coma S brightness profile and estimate its overall extent. Early analyses published by both Chinese and international astronomers confirmed the object S point-like appearance and the presence of a broad, symmetric envelope, with no obvious signs of fragmentation or outbursts during the imaging window. The Tianwen-1 release stands out not just for its scientific content, but for its timing and transparency. By publishing the entire 302-frame series within days of acquisition, the Chinese mission team enabled astronomers worldwide to examine the data, refine orbital calculations, and compare ground-based observations with space-based measurements. The open release also sparked a wave of public engagement. Citizen scientists and student groups began downloading the frames, stacking and processing them to create their own animations, and sharing results across social media platforms and preprint archives. For many, this was their first direct experience working with raw spacecraft data from another planet. In the absence of NASA's higher-resolution HiRISE images, the Tianwen-1 dataset became the primary resource for studying 3I Atlas S appearance during its historic encounter with Mars. While the images do not resolve the nucleus or reveal fine structure, they offer a consistent empirical record of the Comet S behavior at a unique vantage point in its interstellar journey. The Chinese Team S decision to release the full sequence so rapidly highlighted a growing expectation in planetary science that discoveries of rare, high-profile objects should be shared openly, enabling immediate scrutiny and collaboration across borders. 9 distinct anomalies have been discussed in connection with 3I Atlas, each raising questions that remain unresolved in the absence of full, peer-reviewed analysis. Among the most widely cited is the claim of unusually high nickel content reported in preliminary spectroscopic data but not yet confirmed in scientific literature. Early readings suggest elevated nickel to iron ratios, though experts caution that calibration artifacts or low signal-to-noise could explain the result. The object's trajectory, described in some circles as unexplained, is hyperbolic and consistent with an interstellar origin, but minor deviations from gravity, only predictions are still within the range of known cometary activity. No published orbital solution has demonstrated truly anomalous motion. The coma and tail structure have drawn particular attention. Both Chinese and NASA briefings confirm a compact, bright coma with little evidence of jets or filamentary structure. NASA's own statements echo Avi Loeb's early observation of an abnormal tail, but the specifics, a dust-poor composition or unusual brightness profile, remain unquantified. No images to date, including those from Tianwen-1, have resolved the nucleus or revealed fine detail. Even when NASA's HiRISE images are released, the technical limits of orbital cameras at 29 million kilometers mean the nucleus will remain a point source, surrounded by a diffuse envelope. The best available data will allow for improved measurements of coma size and brightness, but not for the kind of surface details some have hoped for. Uncertainties extend to other reported anomalies. Claims of unusual rotation periods, early onset of activity, and unexpected reflectivity are all based on limited or preliminary datasets. Most professional astronomers urge caution, noting that none of these features yet falls outside the range of known comet behavior. The process of scientific validation, calibration, peer review, and cross-agency analysis takes time, especially for rare and distant objects. Looking ahead, the future of interstellar object discovery is set for dramatic change. The Vera Rubin Observatory's legacy survey of space and time will soon begin full operations, scanning the southern sky to unprecedented depth every few nights. Upgrades to the Atlas network, with expanded coverage and improved sensitivity, will increase the odds of catching faint, fast-moving visitors from beyond the solar system. Together, these surveys are expected to boost the rate of interstellar detections from 1 every few years to as many as 1 or 2 per year. Each new object will bring its own set of mysteries and opportunities, reinforcing the need for open data and global collaboration. For scientists and the public alike, the story of 3I Atlas is a reminder that the unknown remains a powerful engine for discovery. Right now, the world's highest resolution images of an interstellar visitor remain out of public reach, not for lack of technology, but for lack of transparency. As new surveys like LSST prepare to spot more cosmic outsiders, public access to discovery becomes the real frontier. In a universe growing less mysterious by the day, withholding data is what keeps us in the dark.